So here's the situation as we left it last time. And basically we have a situation where we, by using integration, kind of prove to ourselves that the, let me get my pen. We prove to ourselves that the force is equal to the current times the resultant length time crossed with the magnetic field. And so we have, this is the resultant length crossed with the magnetic field. And resultant length goes from the beginning of the beginning to the end on our section of wire. And so there is a force on this section of wire. And ironically, as we curl our section of wire round to form a smaller and smaller gap, we get to the point where they touch in a current loop, which is what currents do. They form, you can only get a current when you have a loop. And so when you have a loop, you get this situation where ironically there's no resultant length, and so there's no net force on this loop. So it seems like the effect has gone away. But if we look at this and we say, well, primarily our velocity is kind of down and our B is in that direction. If I do my V cross B, I find that my force is coming out of the board on that side. And if I do my V upwards and my B in that direction, and I do my V cross B, I find my force is kind of going into the page on that side. And so I see, oh, yeah, there's no net force because these two guys are in opposite directions and they're equal in size. So there's no net force, but there is a turning axis. If I was to look at this from above, so now here's my piece of wire, looking at it from above, I would find that this one comes out of the page and that one goes into the page, and so there's a turning axis about there. And so we can get torques out of current loops, even though we can't get a net force out of the current loop. So this next question is designed to kind of test you on this. So it says a current of 9 amps flows along a segment of wire that is shown in the diagram. The magnetic field is uniform and has a magnitude of 12 Tesla. What vector force is experienced by the wire shown in the diagram? So this is an important diagram. We've got to just dissect it a little bit. So I'm showing you an XY plane. These are positions. And I'm showing you a piece of current, a piece of wire lying on the XY plane. It's not linear. And then I'm showing you a magnetic field. And the magnetic field is pointing into the page. We're looking at the tail end of the feathers, so it's pointing into the page. Okay, so what I need to do is I need to figure out what my length vector is. And remember, it's from the beginning to the end of the piece of wire in the direction of the current flow. So because the current flow is pointing in that direction, I go from left to right as opposed to right to left. So that's a... Yes?
So how do you know it's going into? Because it's going that direction?
I mean this B? How do I know it's going into? Because that's that symbol. They have the two symbols. If the magnetic field was coming out, it would be like that.
That symbol is on the exercise already?
That symbol's in your diagram, yeah. Yeah. Oh, yeah. Oh, yeah. No, this is the diagram, yeah. And so when it's coming into the page, it's got an X, and when it's coming out of the page, it's got a dot. So then all I have to do is I say, oh well, what do I know? I know that my B is equal to 12 Tesla, and it's into page. And I know that my I'm going to be using a dot cross product, so then let's write this down. Let's write down B as a vector. So is there any X component for this B? So it's 0I. Is there any Y component for this B? Is it pointing up the page at all? No. 0J. Is there any K vector for this? Any Z vector? Yes. And it's going into the page, which is the negative direction. That's minus 12K Tesla. So that's one skill I need for this. And then the next skill I need is, well, I know my current, I know my I is equal to 9 amps, but of course I want my I want my, and then I know my length, and I need to start at my length. And my length is I put that little dash there to remind me that it is the resultant length. So I have to look at my diagram. And I read it literally from the diagram. Is there an x component for this length? You bet there is. It goes from 2 to 6, which is 4, positive 4i. And then, is there any y component for this length? No, it starts and ends on the same level, so that would be 0j. And then, is there a z direction, a k component for this guy? And no, it's on the plane of the page, so 0k. And that would be meters. So then I say, well, my force is equal to I L cross B. And so I do my I, my J, my K. And then I say, well, I just do it. I say, what's my L? Remember, the order is critical on this. You cannot have B cross L. It's got to be L cross B, or else the answer you'll get is in the wrong direction. So I look at my wording and I go 4, 0, 0. And then I want my B, and my B is 0, 0, and it's going into the page, which is minus 12. So then I do my cross product, and basically I'm going to put my, sometimes I get these wrong when I'm doing them in class because I don't put my thumb physically over what I see, and yet that's the way I was always taught to do them. So I'm going to put my thumb physically over there, and I'm going to go 0 times 12 is 0, minus 0 times 0 is 0. That's 0i. And then minus, put my thumb over that. I go minus 48 minus 0j. And then put my thumb over that. I have 0 minus 0k. Everybody agreed on that? So let's just simplify it. So 0i minus makes plus 48j plus 0k. And now I've got to remember that, of course, that is L cross B, but I want I L cross B. So I've got to multiply this by my current. And my current, of course, is 9 amps. Oh, that's nice. So that's going to be minus I. And then it's going to be 480 minus 48 is going to be 432, I think. J plus 0k. And of course it's a force. It still needs units. Just because I use IJK, it doesn't mean to say it doesn't need units anymore. So I do that. So there we have it. So various skills. Critically, you've got to be able to interpret the diagram. What I find on this is people just don't, they kind of like, they don't pay attention to the direction, so they don't know whether it's into or out of the page, or they don't know how to make vectors out of it. So they don't practice looking at a diagram and saying, what is the IJK for that direction and that magnitude? So it's worth practicing that. It won't always be on the same level. There's nothing wrong with giving you one where they're on 2 different levels, but I wouldn't give you using a diagram, I wouldn't give you a 3-dimensional resultant length. I'd give you 2 dimensions is fine, but not 3 dimensions on that.
B will always be along the z-axis.
No, I can change it. I can actually put my I can mess with it, so I can't guarantee that. But it will be. I could, for example, give you an IJK for that, I suppose. Yeah, I could give you an IJK. It kind of changes the reliance on the diagram, but it's still kind of fair. Yeah, it's quite straightforward. Yeah, cool. So a set of skills on that. It brings together a whole bunch of skills on that. So let's go to the next bit, which is okay. We realize that when we have a coil that's carrying current in a uniform magnetic field, we get a torque. There's a turning effect, and that's really useful because it's the beginnings of a motor. It's not a particularly good motor because it'll turn until The forces are no longer at 90 degrees. Well, turn until the forces are just trying to pull the two parts of the coil apart, and they stop working then. We'll talk about that in a minute. We'll draw that out. So we're going to have to do something about that in our motor design, but that's a secondary issue. Let's just mathematically figure out what this torque is and how we can calculate it. And so I'm imagining a very specific geometry. I don't bother about a curl, a curvy loop. Let's just make a rectangular loop. And I have my magnetic field, and my magnetic field is coming in from the side. It's going all the way through. They only draw, these are the diagrams out of an old version of the book. And they just couldn't be bothered drawing all the arrows in. I guess it's understandable, but don't think it's only that little bit where there's magnetic field. It's all through this. And then they divide this up into 1, 2, 3, 4 different sides. I have to apologize, and I think it's even the latest version of the book. They decide to define their lengths in terms of little a and little b, which is, I think, a little bit problematic because we have big A standing for the area and we have big B standing for the magnetic field. So if you're not careful about your uppercase versus your lowercase, you're in a mess in no time. So just be careful about that. I'm sorry about that. So we say consider a rectangular loop of wire in a uniform magnetic field if we determine the force on each section of the wire in turn. So if we look at this thing here, the current's at the top and the length, this is our length vector, of course, is at the top. And our B is here, so we notice that B is in the opposite direction but along the same line as my L. Yeah? And of course I'm using the equation F is equal to I L cross B. And what I know about cross products is that when the two vectors are in the same direction, either 0 degrees between them or 180 degrees between them, then it's basically the sine of 0 or the sine of 180, which is 0. So I can say, well, just from that observation, there's no force on that piece of the wire because the L and the B are in line with each other. And there's no force along that piece of wire because the L and the B are in line with each other. So that leaves the other two. And I can see in both cases the L, which of course is in the direction of the current flow. So my L is in that direction in that guy. And my B, they're at 90 degrees to each other. So they skip a step. I skip a step, I should say. So F is equal to I L cross B. And when these things are at 90 degrees to each other, it's just the magnitude of L. I can simplify this and say, well, it's going to be I times the magnitude of L times the magnitude of B times the sine of 90, which is 1. So this simplifies to ILB. So I did my cross product very easily there because they're at 90 degrees to each other. And then I say, well, let's put this into the language of this diagram. And the language of this diagram is that my L is A. So I get I, A, little a times B. So that's where that one comes from. And if I'll do the same on this side, although I have my arrow going in the opposite direction, my L is in that direction in this case. It's the same argument holds. And so I have, it's going to be F, I, L cross B. L and B are at 90 degrees to each other, so it's I, L times B, and my L is A again. So again, it's the same force. Opposite direction, we're going to see that in a minute, but the same magnitude of the force. Now, this is important because this diagram is looking from below. If we do our cross product, the L is downwards and the B is to the left on this, and this side number 2. The L is downwards and the B is to the left. V is down, B is to the left. That means that my force is coming out. And so if I drew this from above, I would have the force coming in that direction. And clearly it's not. So this is looking from below. It's just the way they happen to draw it. Makes no difference, just the way they happen to draw it. And so if I look at this, the force is going in that direction. If I look at this end, the force is going that direction. This is a classic torque situation. My force is at 90 degrees to my lever arm, which makes my math somewhat simple. And the lever arm is B over 2 because it's half the width of this, half the length of the bottom piece of wire. And so I say, well, my torque is equal to F2, that's the force on that guy, times its lever arm, which is B over 2, plus F4, that's the force on that guy, times B over 2, plus 0, which goes away. So if I simplify this, it's 2IAB.
Hey, I don't think I deserve that.
Oh, please be quiet. I'm sorry. Well, sure she does, but anyway. So it's F is IAB because we did that up there, so I can substitute in IAB there. And there's 2 of them, so let's put the 2 in front, and the lever arm for both of them is B over 2. So then we end up with I, little a, little b, times the magnetic field. And then I recognize that I is the current and A is the area. Okay. A is the area and B is the magnetic field. Yes?
Does that same thing apply to, say, a circular?
Yes, so the area does, the shape doesn't matter, which is kind of nice.
That's why we started with a rectangle.
Yeah, yeah. It just makes the math easier, yeah. So I can have a long, thin, or a short, wide, as long as the area is the same, it doesn't have an effect. And I could have a circular one or an egg-shaped one, it doesn't matter. Okay, so that's kind of nice. We go to the next case. Well, supposing you're not at 90 degrees to each other, how does that affect things? And if I look at this diagram, all that I'm changing is this B over 2, the lever arm becomes less. The 2 forces remain the same because the 2 forces depend on the magnetic field you've not changed. And the length of the wire perpendicular to the magnetic field that you've not changed. So we're just taking the same coil and allowed it to turn a little bit, and so our forces don't change, but our lever arms do. And so we find that rather than this B over 2, we want B over 2 sine this angle. I define the angle as being my theta. So it's sine theta times B over 2. So I say, well, my torque at an angle is equal to F2 times B over 2 sine theta plus F4 times B over 2 sine theta. Well, combine them. It's 2 times I times A times B times little b over 2 sine theta, which equals IAB times the magnetic field sine theta, which is IAB sine theta. All I've got is I've just got a sine theta term in here. Now, it's the angle that I pick is important, and I've been sort of kind of cunning in the angle that was picked. And what they did was they picked the angle so that I can define this area vector like I did for the Gaussian surfaces. The area vector is perpendicular to the plane of the coil. And I've got to figure out a direction. Does it up or does it down? What's it going to be? But the key thing is the angle between the area vector and my magnetic field. And so I say, oh, if that angle is the angle between my area vector and my magnetic field, I can simplify this as IA cross B. And so I derived a third cross product equation. I had F is equal to QV cross B, that was my first one. And then F is equal to I L dash cross B, that's my second one. And now I'm going to say my torque is equal to I A cross B. So it's the same pattern over and over again. And so how do I know whether this area vector is pointing up and to the right or down and to the left? They're both perpendicular to the area of the plane. And what we do is use a right-hand corkscrew rule. So if you imagine the coil, here I am at the side showing it. If you imagine the coil and you curl your fingers in the direction that the current flows through that coil, then your thumb points in the direction of your area vector. So it's sometimes called a right-hand screw rule, because it's the way that screws work. You twist screws in a clockwise direction, it goes away from you. So it's that. So, okay, that's not so bad. It's kind of relatively easy to remember. There's a lot of right-hand rules in this, but it's relatively easy to remember. So, I'm sorry, I just noticed something on here. So reconnect. Not now. So we'll see. Okay, hopefully that's still going. Yeah, it is. Okay, so fine. That's it. Except, as with all things, when people are working on the same subject for a long time, they tend to take shortcuts. And so what happens is people notice, you know, these two guys, they're always together. The current times the area vector. It's kind of describing what's going on inside the coil. So let's define it by a new term. And so they call it the magnetic dipole moment.